In the last section, we talked about double integrals over rectangular regions. In this section, we're going to build upon that, and we're going to talk about double integrals of two variable functions over more general regions. The easiest way to move forward is to dive right in and start working out some examples. Okay, so let's take a look at this one. We want to find the volume of the region under the surface z equals 5 over 1 plus x squared, and above the triangle in the xy plane with corners 0, 0, 0, 3, 0, 0, and 3, 3, 0. All right, so this is exactly the kind of problem that double integral is great at solving. We want to find the volume underneath the surface z equals 5 over 1 plus x squared over a particular region, right? That's exactly what the double integral does. So we want double integral over the region, the triangular region. We'll deal with that in a moment. Double integral of the surface, so 5 over 1 plus x squared, and we're going to integrate it over the area. Okay? So the hardest part about these double integral problems is dealing with the varied regions that we're going to have. Okay? So it's always a good idea to sketch out the region. So in this case, let's sketch it out in the xy plane. Notice that we can kind of imagine ourselves looking down from above. So we're looking down the positive z-axis, and we're looking down the surface from above. Where would the surface be over? What region are we integrating this surface over? Well, we have one of the corners of this triangle is 0, 0, 0. Another one is 3, 0, 0. So it's 3 on the x, 0 on the y, and then 0 on the z because it's in the xy plane. And then 3, 3, 0. So 3 on the x, 3 on the y. And so we're right about there. Okay, so this triangle is region R. That's the region over which we're integrating. We want to find the volume of this surface between the xy plane and this surface over this region. Okay, so let's start slicing it up. We know how to do this from our previous section. We're going to slice it up in one direction. I'm going to slice it up in this direction. Okay. These are my slices. And so for each slice, now notice, by the way, I'm integrating first with respect to y, right? The change is in the y direction. If I go up or down this slice, I change the y, not the x. I'm holding x fixed. Okay, so I'm integrating with respect to y. Now, from the previous section, we know for each slice, we add up all the values from the bottom of the slice to the top of the slice. And for a rectangular region, that's really easy because every slice would have the same starting point and every slice would have the same ending point. But this isn't a rectangular region, it's a triangular region. Okay? So every slice has the same starting point, y equals 0. But I want to add up all the points until I get to the top of each slice. And the top of each slice changes. It's determined by this line. Okay? And so for different slices, for different values of x, our slices will have a different endpoint at the top. So we want to capture that for every single different slice. So what we're going to do is we're going to use different ways to express the slices based on the x value, the corresponding x value. Okay, easiest way to do this is to find the equation of this line. All right, so this is what, the line 3, 3, 0. So going from 0, 0 to 3, 3, that's the points I go from. And you can see I'm going up 3 over 3, and it's going through the 0.00, this is the line y equals x, right? Up 3 over 3, that's my slope. 3 over 3 is just 1. So this is the line y equals x, okay? So for each slice, I start each slice at 0, and then I end each slice on this line, and y equals x on that line, okay? So we have a variable in our limits of integration, okay? Just in this inner integral. Okay, now once I do that, once I deal with that inner integral, it adds all of these slices up in the y direction, in this direction. Okay, and every slice is added up so it becomes a single value. And so now I just have to worry about the x. Okay, so every one of these slices, this slice here, if I integrate, it's this value, right? For that x, that's what this adds up as. Okay, now I want to add it up in this direction. So I added it up in this direction. Now I want to add it up in this direction. Okay. And so all I'm doing here is I'm taking this shape, I'm squishing it down. Okay, that's what adding it up is. I'm adding up all the little different values on these lines and adding them up so they're a single value. And that squishes them down to lots of values to a single value for each slice there is. Okay. And now I want to add up. I've squished it down this way. Now I want to squish it down that way by adding it all up in that other direction. Okay, so I'm going to go for farthest x here to farthest x here. Okay, so that's x equals 0 to x equals 3. I could see by which points I projected down. Okay, that's setting up the integral. I want to point out that this inner integral here, notice it's from y equals 0 to y equals x. It's from this bottom boundary to this top boundary, because for every single slice, the bottom of each slice hits that bottom boundary y equals 0. Okay? The top of each slice hits that top line y equals x. And so I'm able to integrate each slice individually by making the slice, the limits of integration, dependent on x. Notice that the inner integral can only be dependent, that the limits of integration of the inner integral can only be dependent on variables outside of it, further out. Okay? So why can the limits of integration here can be dependent on x, because dx is still further out. I haven't dealt with it yet. Okay? But I can't have these limits of integration be dependent on y. I've already dealt with that in the inner integral. Okay, so just be aware of that. You could only deal with variables if they are further out of your limits of your integration. Okay, so I can deal with x, but x can't deal with y. Can't use y and its limits of integration, or itself, by the way. You cannot use your own variable. I'm integrating with respect, I can't have limits in terms of x. Okay. All right, let's integrate. I'm going to integrate first with respect to y. Okay. So with respect to y, I treat all this as a constant, so I'll just throw in a y. Right? Integral of a constant is a constant times y. I'm going to evaluate that from y equals 0 to y equals x. So I plug in x, my top limit, and I subtract what I get when I plug in 0, my bottom limit. Okay? Now, of course, this is just 0. So I have the integral from 0 to 3 of 5x over 1 plus x squared integrated with respect to x. Okay? This is a calculus 1 integral. Pretty simple u substitution. I'm going to let u be 1 plus x squared. Derivative of u with respect to x is 2x. Let's put all my x's on one side, all my u, everything else on the other. So that would be du over 2 equals x dx. So I can swap out x dx with du over 2 to make this substitution work. And I have that. I have an x dx. Okay? So I still have the 5 up there. The x dx becomes du over 2. I'm going to put the over 2 bit out in front of the integral. Okay, so du over 2. And then in the denominator, 1 plus x squared, that's my u. Because I have changed my variable from x to u, my limits of integration also change. When x equals 0, u is going to be 1. When x equals 3, u is going to be 10. So where x went from 0 to 3, u goes from 1 to 10. Okay? Antiderivative of 1 over u is natural log of u, and I'll just pull the 5 out front. So I get natural log of, technically it's the absolute value of u, but we're only integrating over some positive values from 1 to 10. So you could drop the absolute value. So I get 5 halves natural log of 10 minus natural log of 1. Natural log of 1 is 0. Okay. Which means I just get 5 halves natural log of 10. That is the volume of this surface. Z equals 5 over 1 plus x squared over this triangular region. Okay? We did it using a double integral. Now, I do want to point out that we went with a particular order of integration. Okay? We integrated first with respect to y and then with respect to x. We don't have to. We can choose to integrate first with respect to x and then with respect to y. Let me show you what that looks like. Okay. So we still want the double integral over the region of 1 over 1 plus x squared integrated over area. Our region is exactly the same as it was before. 1, 2, 3. 1, 2, 3. Okay. But I'm going to slice it up in a different direction this time. Okay. Let's slice it up this way this time. Now, if I'm slicing it up this way, then which way would I be integrating? I'd be the change on each slice. The change happens as I move left to right. Right? And so the change is in the x direction. So if I'm going to slice it up this way, I'm going to integrate first with respect to x. And I think I got the integrand wrong, right? It should be a 5 up here. So I'll integrate first with respect to x, which means I'll have to integrate after with respect to y. Okay? Now, if I'm going to slice it up in this direction, the x direction, where does my x range from? For each slice, what's my lowest x? What's my highest x? So for each slice, the left edge of each slice is along this line, which we already found was y equals x. Okay? So the beginning of the integral, the first limit of integration, needs to be this slice. Okay? And because I'm integrating with respect to x, it needs to be x equals something. In this case, this edge would be x equals y. So if I'm integrating with respect to x, I'm going to start it with y because that's the beginning of each slice. And then I integrate and I add up all the points along each slice until I get to the right edge of each slice. And the right edge of each slice is going to be on this vertical line, which is the line x equals 3. So I go from x equals y, this line, to x equals 3, this line. Notice the limits of integration always have to be in terms of this variable. That is, it needs to be x equals y, x equals 3, because I'm integrating with respect to x. Okay? So the limits need to be x equals something. Once I integrate in that direction, okay, that adds up all my x's together, and I'm squishing it like that. Okay? All the values on this line get squished into a single value. And that happens with every line there is. Okay, so all gets squished, so it's the only change is now in the y direction. There's no more change in the x direction. Okay, and so now, once I get rid of the x, once I've reduced the dimensions and found the projection of the shape, squished it down onto the remaining axis, the y-axis, where does this go from and to? Well, it goes from y equals 0, right? Y equals 0 to y equals 3. Okay? Notice what I said before. The inner integral, the limits of integration can depend on variables that we deal with outside of that integral. So we integrate with respect to y outside of the inner integral. So the limits of integration can have y in it. But once I'm outside, I cannot use variables inside in the limits of integration. So these variables cannot be written in terms of x because x is in the inner integral. I've already dealt with it by that point. Okay? There's no variables left, so they have to be constants. Your outer limits of integration always has to be just numbers, just constant values. Okay? They cannot depend on the variable you're integrating with respect to or any variable that you have already integrated with respect to. Okay? All right, so let's do the integral. Now you may notice right off, this integral is harder. Do we know the integral of 5 over 1 plus x squared off the top of our heads? Well, maybe you do, but it is a calculus 2 integral. It's a little bit harder. There's a couple ways you could approach it. You can use trig substitution if you want, or you could just happen to know what it is. This is a common enough integral that I actually know what it is off the top of my head. The 5 is a constant, it comes along for the ride. And the integral of 1 over 1 plus x squared is the arctangent of x. Okay? And I'm going to evaluate that from x equals y to x equals 3. Okay? So let's plug in. Integral from 0 to 3 of 5. Plug in that top limit first. Arctangent of 3. And you know what? Let me move that 5 outside the integral. It's just a constant. Make things a little bit easier to look at. Arctangent of the top limit first minus arctangent of the bottom limit. Okay. Okay. I mean, awesome. How do I integrate arctangent of y? That'd be the next thing I'd have to integrate, right? I have to integrate with respect to y. How do I integrate arctangent of y? Well, the short answer is it's hard to find. You can use integration by parts to find it. I'm just going to give it to you. Okay. So arctangent 3, that's just a constant. So if I integrate that with respect to y, I get the constant times y. Integral of arctangent of y, make sure I put the negative out there. It is x arctangent, I'm sorry, not x, we're integrating with respect to y. Y arctangent of y minus 1/2 natural log of 1 plus y squared. I'm going to evaluate that from 0 to 3. Okay, that's not easy to find. I do not expect you to find it. My point of doing this is to show you that there is a difference, a big difference in which variable we decide to integrate with first. Okay, sometimes one integral is just really hard. Okay, and then the other integral is pretty straightforward. And it's not always obvious when you first look at it. So if you're doing a double integral and you integrate with respect to one of your variables and it's just ridiculously hard, try to integrate with respect to the other one, okay, first. So here we're integrated with respect to x, then with respect to y. It's really hard. I'm going to finish it off just so you can see that we do get the same thing. But doing it this way is definitely the harder way, right? So I'm going to plug in the top limit first, which is 3. So I get arctangent of, you know what, let me put that y in front. So 3 arctangent of 3. Plugging 3 into the y, and I just stuck it in front there. Minus, because I notice it's going to be the same as this, 3 arctangent of 3. Minus 1/2 natural log of 1 plus 3 squared. That's going to be 10. Okay. Boom. And now subtract what I get when I plug in 0 minus 0 arctangent of 3 minus 0 arctangent of 0 minus 1/2 natural log of 1. Okay. 0 times arctangent of 3 is just 0. 0 times arctangent of 0 is just 0. And natural log of 1 is also 0. Value that's worth remembering. Natural log of 1 is equal to 0. Okay, so all of this just cancels out, which is good. Okay. And then we got 3 arctangent of 3 over here, and then minus 3 arctangent of 3. Okay, so if I distribute this negative, 3 arctangent of 3 and 3 arctangent of 3 goes away. I have a 5 out here. I have a 1/2 here. Because I distribute the negative, it becomes positive. So I get positive 5/2 natural log of 10. Okay, and as you can see, it really is the same value, just a much harder way to do it. Okay. So generally, you can integrate either way. A lot of times, one direction will be easier than the other. Sometimes it will be clear from the region of integration whether you want to integrate first with respect to what x or with respect to y. Sometimes you just have to dive right in and try one method. Here we integrated with respect to y first, and it worked out great. And then if we integrated with respect to x first, we end up having to integrate arctangent, which is really unpleasant to integrate. Okay. If we had gotten here, I probably would have said, hey, let's go back. Let's try integrating the other direction. Okay. But theoretically, both directions of integration will give you the same thing. Let's take a look at another example. We want to find the volume under the surface z equals 3xy and over the region bounded by y equals x cubed, y equals x cubed plus 1, x equals 0, and x equals 1. So this is a similar problem to the last one. We want to find the volume underneath the surface z equals 3xy. We want to integrate this over a particular region R bounded by these functions. And we're integrating it with respect to area. Okay. As with previous problems, The region is going to be the key here. So I'm going to focus on drawing out that region. Okay, again, we're just focusing on the xy plane because this region lives in the xy plane. So y equals x cubed. Hopefully we know what that looks like. Looks kind of like this. You don't need to be exact, but having a rough sketch is good. Okay. So it's y equals x cubed. Then I have y equals x cubed plus 1. That is the same curve, but it just shifted up 1 unit. So take all my points, shift them up exactly 1 unit, and draw the same curve. Okay. That's y equals x cubed plus 1. And then I am also bounded by x equals 0 and x equals 1. So x equals 0, that is the y-axis. And x equals 1. That's this line right here. Okay. And so this is the region which I want to integrate over. Okay. Let me blow it up a little bit just so we could see it a little bit better. Okay, so this is the region. Okay. Now, one of our first choices we need to make when integrating over a region is, should we integrate with respect to y first or with respect to x first? Sometimes it's hard to decide, but a lot of times one way is definitely easier to work with the region in. Okay. In this case, I would want to integrate with respect to y first. Why? Well, let me show you. Okay. If I slice it up in the y direction, that means I'd be integrating with respect to y first. I would want to find the edges of each slice, the bottom and the top of each slice. Okay. In this case, the bottom of every one of my slices can be described by the same curve, right? The curve y equals x cubed. And the top of every one of my slices can be described by the same curve. Y equals x cubed plus 1. That's going to be a big advantage because if I try to slice it up the other way, in the x direction, letting the x change and holding the y fixed for each slice, the left edge and the right edge of each slice change. I have to use different functions to describe them. Okay. Up here, this function y equals x cubed plus 1 describes the left edge of each of these slices, right? But down here, it's this line x equals 0 that describes the left edge of each slice. Because I have two different ways to express my left edges, if I was going to integrate first with respect to x, I would need to slice it up right here and use two double integrals, one to deal with the top region and one to deal with the bottom region. And I would prefer not to do that, right? I don't want to do two integrals when I can just do one. All right. So we may see an example of that, but right now we are going to integrate first with respect to y, because I can use the same curve to describe the bottom of every single slice, and I could use the same curve to describe the top of every single slice. Okay, so I've chosen to integrate first with respect to variable y. And that means x goes second. So dy dx. So this inner integral, I'm integrating with respect to y, so I need this to be y equals something. I need this to be y equals something. These should represent the bottom and top of each slice. In this case, it's pretty straightforward. The bottom of each slice is represented by this curve. This curve is described by y equals x cubed. And so that is my lower limit of integration. That's how I describe where the bottom of each slice is. Okay? The top of each slice is up here. Again, just one function, and the curve is written y equals x cubed plus 1. So y equals x cubed plus 1 is my top limit of integration because it tells me where the top of each slice is. Okay? Now I integrate it with respect to y. I integrate it in this direction. And that takes every one of those slices and integrates them in this direction, adds them up in that direction, which means it's squeezing it down in the y direction. All of these values along this line, I'm adding them all up to be a single value. So after I integrate with respect to y, the y is gone. So I only have the x-axis left. I only have the one variable left. Okay, all these values have been squished down into this. And so now I need to determine the bounds for x. So this goes from x equals 0 to x equals 1, right? Because remember this line, this vertical line was x equals 0, this vertical line was x equals 1. So I integrate my outer limits from x equals 0 to x equals 1. Now, little sanity check. Remember that an integral should not depend on any variables that you are integrating with respect to or that you have already integrated with respect to. Okay? So these limits of integration should not depend on y, and indeed they don't, right? They depend on x, but not y. And that's okay because I haven't integrated with respect to x yet. As I work my way outward to the outer integral, by the time I get here, the limits of integration can't depend on y or on x. And indeed they don't. They are just constant values. They do not depend on variable y. They do not depend on variable x. Okay? All right, so now let's actually take the integral. This is actually usually the easier part. We are comfortable with integration, and so let's actually integrate this. Usually the methods we use to integrate this shouldn't be much more than what we need to integrate in Calculus 1. All right, so I'm going to integrate this with respect to variable y. I'm going to hold x constant. So the constant comes along for the ride. Integral of y is y squared over 2. And I'm going to evaluate that from y equals x cubed to y equals x cubed plus 1. When I'm all done, I'll integrate the result with respect to x. Okay? All right, I'm going to pull out the 3/2. That's just a constant with respect to all the integrals. So I can pull it all the way out to the front. Can't do the same with the x because it's a constant with respect to the inner integral, but not the outer integral, right? So I can't pull it all the way out. It has to stay in here. But let's see what I have. After pulling out the 3/2, I have the x, and then plug into the y. So top limit is x cubed plus 1 squared minus x, and then plug into the y. The bottom limit is x cubed squared. Integrated with respect to x. Okay? All right. How do we do it, this integral? Well, it's not pleasant, but it's not hard. we just have to FOIL this out, combine like terms, that kind of thing. Okay, if I FOIL out, if I expand out x cubed plus 1 squared, I would get x to the 6 plus 2x cubed plus 1. And if I multiply all this together, x cubed squared is x to the 6th times x is x to the 7th. Okay. Distribute that x, combine like terms. Here, this first distribution, I get x times x to the 6th. That'll be x to the 7th. Minus x to the 7th, they'll go away, right? Leaving me just x times 2x cubed is 2x to the 4th. And then x times 1 is x. All right. So that was simplifying the integrand. Now let's actually integrate with respect to x. Integral of 2x to the 4th with respect to x, I get 2/5 x to the 5th. And integral of x is 1/2 x squared. And I'm going to evaluate that from 0 to 1. If I plug in 1, I get 2/5 plus 1/2. And I'm not even going to bother plugging in 0. If I plug in 0, this all goes to 0, right? So I guess maybe I'll just write minus 0. And just tidied up, combine like terms. 2/5 is the same as 2/5 is 4/10. And 1/2 is 5/10. So what do we get there? 9/10. 3/2 times 9/10 is 27/20. That is the volume underneath the surface over this region here. Take a look at another example. Here we want to find the volume under the surface z equals xy plus y and over the region R bounded by these two curves. So this is exactly the same as what we have been doing. And this is exactly what a double integral is good for. So we want to find the volume under the surface and over a certain region. So we want to find the integral of the surface xy plus y over region R, and we want to integrate over the area of R. Now, as with other double integral problems, the trick here is finding the region of integration and the bounds that correspond to that region of integration. So let's sketch out the region that we're dealing with, the two curves and the region that they create. So we have the curve x equals y squared plus 1. That is going to be a parabola sitting on its side horizontally. Opens in the positive x direction, but it's shifted to the negative x direction 1 unit. So we're shifting it 1 unit to the left. So instead of having the vertex here, we shift it 1 unit left over here. Okay, and so we get a parabola. That looks like this. Okay, x equals y squared minus 1. Now, the graph of this function is one that you should know, but maybe you don't know it yet. Okay, this one is worth knowing, though. It's actually half a circle. Okay, and to see that, let's square both sides. So I get x squared equals root 1 minus y squared. Except I lost the root, I squared both sides. So x squared equals 1 minus y squared, no root. If I add the y squared to the other side, I get x squared plus y squared equals 1. So you could see we get a circle of radius 1 centered at the origin. Okay. Now, going from this step to this step, squaring, we lose some information. Okay, when you square something, you lose sign information. This is positive x, I squared, I get that. If this is a negative in front, I square both sides, I get the exact same thing because once I square it, I lose the sign information. Okay. In this case, x is equal to a positive root. So we want the portion of this circle of radius 1 that where x is positive. So we want the right half of a circle. So we want a circle of radius 1, but we only want the right half of it, only the portion where x is positive. Okay. So that was x equals square root of 1 minus y squared. Okay. So this is the region that we're dealing with here. Region R. What we need to do now is decide how we're going to slice this up. Are we going to integrate with respect to x or with respect to y? Okay. What we want to do here is we want to integrate with respect to x. We usually want to pick the direction of integration that is going to make things easiest. Sometimes it's not clear that there is an easiest direction. Sometimes they seem to have the same difficulty either way. Right? This is not one of those cases. There's definitely one direction where it's going to be easier to set up the limits of integration. And that is if we integrate with respect to x first. So we're holding y fixed. We are letting the x change. So the slices are horizontal. All right. We like integrating this direction because we can describe the beginning and end of each slice using the same curve in each case. All right. So for each one of these slices, if we look at the beginning of each slice, then every one of those beginnings is on the parabola. And so we can describe the beginning of each slice on that parabolic curve. Okay? And the end of each slice is going to be on the edge of the circle. And so I could describe the end of each slice using the same curve. Now let's compare that to slicing it up in the other direction. What if we were to slice it up in the y direction? We slice it up in the y direction. Notice where the slices begin and end. Right now, they're beginning on the bottom half of the parabola and ending in the top half. But once I move over here, I begin on the bottom half of the circle and end on the top half. Because of that, I would have to split this into two different integrals. I'd have to do one integral over here where each slice begins on the bottom half and ends on the top half. Those would be my limits of integration. And so I'd use one integral to find the volume over this shape. Okay. But then I'd need a different integral over here because these slices begin and end on a different curve. So I would have to describe them differently. And so I'd use a different integral, different double integral, to integrate over that shape. So I'd have to do two integrals if I wanted to integrate in this direction. Okay. Now sometimes even if integrating one direction seems easier than the other, sometimes the integrand itself is easier in one direction than the other. So it takes some guesswork, and if you plug in the limits of integration for one direction and the integrand isn't cooperating, it's hard to take the integral, try the other direction. In this case, though, it does look like the integrating with respect to x first is the easier approach here. Okay, so we're going to try that first. Now, if it doesn't work, if the integrand gets too difficult to work with, then we could swap it up. We could start over and try integrating with respect to y. But for now, we're going to try integrating with respect to x first, holding the y fixed for that inner integral, and integrate with respect to x. So I'm going to integrate first with respect to x, which means that y will be second. Okay, so I want to focus on the inner integral first. I want to look at the limits of integration. For each slice, my bottom limit should be the beginning of the slice, where the slice is more negative. In this case, where we're horizontal, that'd be further left. So I want the left edge of each slice to be my lower limit of integration. And I want the right edge of each slice to be my upper limit of integration. Okay? And because it's dx, it needs to be dx equals something. X equals something. The somethings are what go there. All right? So in this case, that left edge for every single one of those slices is going to be the parabola, which is x equals y squared minus 1. So that is my lower limit of integration there. And the right edge of every single slice is the curve x equals root 1 minus y squared. And so that's going to be the top limit of integration. Okay. Once we have dealt with that, we have taken each one of the slices and added up all the values into a single slice. Okay, so every one of the slices has collapsed into a single value. And we get rid of that dimension. So we had an x and a y axis by adding up in the x direction, by integrating in the x direction. We add up all the values in the x direction, collapse it into a single value. Okay, every one of the slices into their own single value. And now we want to add up in the other direction. We want to integrate in the other direction. Okay, so we've squished that shape down in the x direction by integrating it. And now all we're left with is the y direction. Okay, so notice every integral you effectively reduce the number of dimensions. Okay, so we start with 2 dimensions, we integrated with respect to x, it collapsed that dimension, added up all the values in that direction. Okay, and left me with only the one dimension left, the y-axis, right? The y goes from the lower point here. This is circle of radius 1, and we can kind of see they intersect on the y-axis. So y equals -1 to y equals +1. Okay? Y equals -1 to y equals +1. So those are my limits of integration. Just a quick sanity check. Make sure that our limits make sense. We want to make sure that that for each integral, the limits of integration only depend on variables we haven't integrated with respect to yet. Okay, so here we're integrating with respect to x, but we haven't integrated with respect to anything else yet. So these limits of integration cannot depend on x. And indeed they don't. They depend on y, but not on x. And y is okay. We haven't integrated y yet. It's over here. So it can depend on y. That's okay. So those make sense. Okay? And then when we reach our outer integral, now I can't depend on y or on any variable I've already integrated. So it can't depend on y or on x. And indeed they don't. They don't depend on any variable. So we're good there too. So our sanity check, everything looks like it's okay. All right, let's actually integrate. Generally, the hardest part of these problems should be setting up the limits of integration. If when taking the integral, it just seems really hard, try swapping the order of integration. So right now we're integrating with respect to x first, then with respect to y. Now, if this gets too hard, what we might do is we might go back and we say, you know what, maybe this wasn't the right approach. Let's try integrating in the other direction, integrating y first and then x. Okay, in this case I don't think it'll be a problem, but just be aware that that's always an option. All right, so integrating with respect to x, integral of xy, I get 1/2 x squared y, and integral of y, I get xy. Treating y as a constant, only integrating the x. I'm going to evaluate that from x equals y squared minus 1 to x equals root 1 minus y squared. Okay, so let's finish this up before we do that outer integral. So I want to plug in my limits of integration into the x. That's the variable we integrated. Okay, so I get top limit. I get 1/2 root 1 minus y squared times y. Just plug that into the x. And then here, same thing. Plug root 1 minus y squared into the x times y. Minus, and then plug in the bottom limit, y squared minus 1. So I get 1/2, plug y squared minus 1 into the x. And one more time. Okay. All right. Let's see what we can do with that. We want to simplify that before we try taking the integral. So inside here, I get 1/2. I'm going to move this y over here to the front. And then the square root squared. Square root goes away. I just have 1 minus y squared. Plus, I'm going to do the same thing here. Just move the y to the front of the term. Y root 1 minus y squared. Minus 1/2, move the y to the front, y squared minus 1 squared plus y times y squared minus 1. Okay, so to fully simplify this, we're going to want to multiply all this out. Okay, so I get 1/2 y minus 1/2 y cubed. Just distributing this in. Okay, now here there's not much I can do. It is what it is. So I'm just going to leave that as it is. Now in here, y squared minus 1, that's, if I follow that out, that'd be y squared minus 2y plus 1. And then multiplied by the half y, I'd get 1/2 y cubed minus y squared plus 1/2 y. And then here, distribute that also. I get y cubed minus y. Okay, combine like terms now. Just so I don't get mixed up, I usually like to go from highest power down to lowest. Okay, so let's deal with the, looks like the highest power is a cube. So I get negative 1/2 y cubed, negative 1/2 y cubed, and negative y cubed. So that would be what? Negative 2y cubed. Okay. Next power down would be y squared. And it looks like I just have the one y squared term, so that'd be a positive y squared once I distribute that negative. Power y to the power of 1, I get 1/2 y minus 1/2 y plus a y. So that would be just y. And then next would be constant values, but I don't see any constants. And then finally, let's not forget about this guy because it really doesn't fit anywhere else. So plus y root 1 minus y squared. Okay. Now this actually is a pretty straightforward integral now. Mostly it's just power rules here. Here I will have to do a substitution. So I'm going to split this into two integrals because over here I can integrate this without any substitution or anything. Okay. And then the root I'll put under a separate integral. So I could do the substitution just for the root. Okay, so here I get negative 2y to the fourth over 4. That simplifies to negative 1/2 y to the fourth. Integral of y squared is 1/3 y cubed. Integral of y is 1/2 y squared. And I integrate that from -1 to 1. Okay. Now over here, I need a substitution. So I'll do u equals 1 minus y squared. The derivative of u with respect to y is -2y. I like to put all my y's on one side, everything else on the other. So negative du over 2 equals y dy. So as long as I have a y dy, I can swap it out with an expression involving du, and that's what I would need to make the substitution work. So y dy is what I will get rid of. That would become du over -2. So let's turn this positive to a negative, and then the -2 denominator, I'm just going to pull out to be a -1/2 in front. Okay, and then root minus y squared becomes root u. And then u goes from, if y is -1, then u starts at 0, right? If I plug -1 in there, I go from 0. And if I plug in 1, well, if I plug in 1, 1 minus 1, hey, that's also 0. Well, that's interesting. What does that mean? Well, the area from 0 to 0 is 0. Okay? What's going on here is that this function, if you actually looked at it closely, is symmetric. Okay, it's an odd function. And because we're going from -1 to 1, the area from 0 to 1 and the area from -1 to 0, they'll cancel out. Okay, so we don't have to go any further than that. As soon as we recognize that the limits of integration are the same here, that's 0, that whole integral is done. Okay, and then here, just plug in, finish it off by plugging in here. -1/2. If I plug in 1 to the 4th, 1 cubed, 1 squared, it's just all 1. So I just get -1/2 plus 1/3 plus 1/2. And if then I subtract what I get when I plug in -1. -1 to the 4th is just 1, so I get -1/2. -1 cubed is -1, so I get -1/3. And -1 squared is +1, so I get +1/2 again. Okay, so most of this cancels. -1/2, +1/2, -1/2, +1/2. I just have 1/3 minus -1/3. That's going to be 2/3. That's my final answer. Okay. So I want to emphasize again, all this was a lot of work, right? Here on down, fair bit of work. But there was nothing dramatically new in what we were doing here. These are Calculus 1 integrals. Most of the new work that we had to think about was finding those limits of integration over a multivariate region. Okay. So I want to take the same problem and I just want to set up the integral going the other direction. So here we integrated first with respect to x, then with respect to y, right? We thought a little bit about integrating first with respect to y, then with respect to x. We kind of ruled it out because we'd have to split it into 2 regions. I want to show you what that would look like, okay? Now we won't evaluate the whole integral, we'll just set it up. Let's just recreate our region very quickly. So we had the parabola. And that was x equals y squared minus 1. And we had the half circle. Okay, that was x equals root y 1 minus y squared. Okay, so we just integrated this first with respect to x, then with respect to y. Let's see what happens if we set up the integral the other way around. What if we integrate first with respect to y, then with respect to x? I just want to show you what this looks like. Okay. And let me move this so we can actually see it. Okay. Now, as we had already discussed, if we integrate in this direction, we would have to split the integral into two pieces. Okay, we'd have to do this piece here because the slices here start on the bottom half of the parabola and end in the top half of the parabola. Okay, and then this piece here we'll have to do separately because the slices here don't end and start on the parabola. They start on the bottom half of the circle and they end on the top half of the circle. We describe the beginning and end differently. Because of that, we have to do two different integrals. Okay, so let's do the left half first. The surface stays the same, and we're going to integrate because we're moving up and down, right? That's the y that's changing, and we're holding the x fixed, so we're integrating first with respect to y. So this is for the left side over here, okay? So we want, and then so dy then dx, so let's focus on the y. So we want y equals the bottom value of y and then the top for each slice on the left half. Okay. So for each one of these slices on the left half, they start with the bottom half of the parabola. Now the parabola is x equals y squared minus 1. That's written as x equals something. I would need it as y equals something since I'm integrating with respect to y, right? So let's take this and rewrite it in terms of y. Okay, so x equals y squared minus 1. If I move the 1 over, I get x plus 1 equals y squared. And then I need to take the square root. Y equals plus or minus root x plus 1. That plus or minus is going to be important because the minus is giving us the equation for the bottom half of the parabola. Okay, so y equals negative root x plus 1. And then we go to the top half of the parabola. Okay, each one of these slices on the left side ends at the top half of the parabola. That's y equals positive at root x plus 1. Okay, because in both cases it's a parabola, so it's the same equation. But the bottom half is where y is negative, so we use the negative root. The top half is where y is positive, so we use the positive root. Okay? Now, once we do that, we collapse that portion of the region. I didn't really leave enough room for this. Maybe I'll write it down here. Okay? So this was x, this was y. We integrated with respect to y, so we add up all those values and add them up into a single value, collapses them. We flatten it, but only the left half. Only that half. Okay, and we could see we're from -1 to 0. X goes from -1 to 0. Okay, so that's going to give us part of our answer, that double integral. That gives us the volume over that portion of the region. We would separately have to deal with this portion of the region. So add another integral that deals with the right portion. So it's still the same surface. Okay? But now we want to deal with the right portion. So each one of these slices starts at the bottom half of the circle, ends at the top half of the circle. Okay? This is the equation of the circle, but similar to what we've done before. If we're integrating with respect to y, it needs to be y equals something, and y equals something. Okay? Right now, we're describing this circle as x equals something. So we need to figure out what it would be as y equals something. Okay, so let's sketch it out right here. Square both sides. We need to get the y by itself. add y to the other side, subtract the x. I need to get the y by itself on one side. Take the square root of both sides. And make sure you consider all the roots. So y equals positive and negative root 1 minus x squared. The positive would be where the y's are positive. That's the top half of that circle. The negative are where the y's are negative. That's the bottom half. So that's going to give us our limits of integration. We want to go from the bottom half of the circle, y equals negative root 1 minus x squared, to the top half, y equals positive root 1 minus x squared. Okay? Once we integrate in the direction of y, we add up every strand so it's a single value. Okay? We collapse in that dimension. Putting us only in the x axis. Okay? Limiting us to one dimension, just the x axis. Okay? And so this shape over here collapses into just this, this region in one dimension. And we can see that goes from 0 to 1. So x, the outer limit of integration here, goes from 0 to 1. Okay? So we could find the integral of this. We could find the volume by doing two double integrals here. And we would get the exact same answer, by the way. We would get negative 2/3. Okay? I won't actually do all the integration here, but we would get 2/3. As a rule, your first attempt should probably be the simpler integral. Okay? So that's why we integrated with respect to x first. That was our first try, because we could integrate with only one integral. Now, if you start integrating, you're like, gee whiz, this integral is really hard. I don't know how to integrate this. Then you could try switching it up, switching the order of integration. Sometimes we need to integrate it with two separate integrals because that's just the way it's going to work, even if we do have to do it with two integrals. Okay? So just be aware both options are possible. So try to pick the easier option to start with. You could always go back to making it more complicated if you need to. Let's take a look at one more example. Here we're given a double integral. We want to reverse the order of integration. This is a good exercise for practicing how to work with these limits of integration for multiple variables. Okay? So the very first thing we need to do is we need to take the limits of integration we already have, and we need to sketch a region using them. Okay? This is definitely not as simple as just taking this integral and putting it on the outside and taking this integral and putting it on the inside, right? Because this inner integral depends on x. If we take the x and move it on the inside and take this integral and put it on the outside, that's going to be a problem, because the outer integral cannot depend on any variables that we've already integrated with respect to. Okay? So it's not as simple as just swapping the two integrals. We have to be very careful about what our new limits of integration are. Okay, so let's start by taking our current limits and sketching a region with them. Okay, so these current limits tell us the bounds. We want y to go from x squared over 2 to x. So our current bounds are y equals x squared over 2 and y equals x. Okay, and then our outer integral, the bounds are x equals 0 and x equals 1. Okay, so let's graph the region with these boundaries. We have y equals x squared over 2. That is a parabola. It's squished down a little bit because I'm dividing by 2. So its vertex is at the origin. And then if I plug in if I plug in 1, I'm just at a half, right? Same thing with -1. If I plug in 2, I'm at 2. So that's my parabola y equals x squared over 2. Okay. Then I have y equals x. So that's just a line. Goes through this point and this point and this point. Line of slope 1 going through the origin. Y equals x. And then I have x equals 0 and x equals 1. So x equals 0 is the y-axis. And x equals 1 is this line right here. Okay. So what region are we integrating over? So it looks like there's lots of little enclosed regions, right? We've got this region, and this region, and this region. There's actually only one, though, that's enclosed by all of these. And that's this one right here. Okay, it's enclosed by this line and this line. We have to stay between these two lines. Okay, and then between these two curves. The axis here isn't a boundary for our region. Okay, so it looks like there's a little region right there. It's not. Okay, because that's an axis, not a boundary. Okay, so this is the region we want here, that little region there. Right now, we're integrating first with respect to y and then with respect to x. So right now, we're slicing things up in this direction. Integrating first with respect to y and then with respect to x. We want to flip the order of integration. So we want to integrate first with respect to x and then with respect to y. So we want to slice it up this way. Okay. As we do, we may realize that things are going to get a little more complicated if we change the order of integration. Because notice the right edge of our slices, if we integrate first with respect to x, changes. Down here, the right edge is the parabola. But up here, the right edge is the line x equals 1, right? So we are going to have to split this into two integrals since the right edge of our slices changes. Okay, so I'll have to do one integral for this lower half and one integral for the upper half. Okay, let's do the lower half first. So we're changing our order of integration. It was dy dx, so it's going to be dx dy. We're slicing things horizontally. That means the x is changing. We're holding the y fixed for that first inner integral. So this is going to be the lower half, that first integral. And then we'll do another integral that separately deals with the upper half. Okay, actually, let me move where I write those. Lower half, upper half. Okay, so let's do the lower half first. For the lower half, what we want to do first is we want to go, so we're only worried about this half here. Okay, maybe I can make this a little more noticeable. There we go. Okay. So we want this lower half here. So we're going to go from the left edge of each one of these slices to the right edge. Those are going to be our limits of integration for our integral in the lower half. So the left edge is the line y equals x. The right edge is the line y equals x squared plus 2. Now we're integrating with respect to x. So we want our limits to be x equals something. Okay. Now for this left limit, that's no problem. We have the line y equals x. Okay. Y equals x means x equals y. So our left limit here is x equals y. Okay. But for the right limit, we have this parabola. We have it written as y equals x squared over 2. We're going to have to rewrite that as an x equals something. Okay. So y equals x squared over 2. I need to get the x by itself, so multiply the 2 to the other side, take the square root. I have 2y equals square root of 2y plus or minus square root of 2y is equal to x. Okay, now that gives us two results, right? X equals positive root 2y and x equals negative root 2y. Which one do we want? Well, the negative is where the x is negative. It's the left half of the parabola. Okay, the positive is where x is positive. That's the right half of the parabola. We definitely want the right half of the parabola, right? So we want x to be positive, so we want it to be equal to the positive root. So x equals positive root 2y. And that's for my lower half. That tells me the beginning and the end of each slice. Okay. Now, once I do that, I've integrated it in the x direction. That collapses that dimension. I only have to worry about y now. But only y for that bottom half. Okay, I'm only dealing with the bottom half. Okay. So I can see the lower y now if I'm doing the limits in terms of y with what's left. I can see the lowest y for this bottom half region is 0. A little bit harder to see where this is, right? But I can see it's going to be at this point here, right? That's kind of where we change. That's the upper half of my lower region, or I'm sorry, the upper limit of my lower region. And that's going to be where the parabola and the line x equals 1 intersect. Okay? So if I just plug in x equals 1 here, I could find my limits. If I plug in x equals 1, I get y equals 1/2. So I'm going to y equals 1/2. Okay? And those are my limits in terms of y. Y equals 0 to y equals 1/2. All right? That's the bottom half done. I've swapped the order of integration for that bottom half of the region. Okay? Now I need to do the top half. So for this top half, same idea. I'm integrating first with respect to x, so I'm letting the x change. That gives me horizontal slices. Okay? For each slice, I'm going from left edge to the right edge, and they need to be x equals something. The left edge is the line y equals x, which means, just flip that around, that's x equals y. And for the right edge of each one of those slices, I'm going up to x equals 1. So x equals 1. Okay? And then once I do that inner integral, that collapses that dimension, and I only have to worry about what's left in the y direction. So slap it all onto the y axis, project it onto the y axis. Okay, so that's the top half there. And we could see it starts at 1/2, kind of makes sense. It starts, the upper half starts where the bottom half ended, right? Right here. And it ends right here. That's going to be where x equals 1 and y equals x. where those two intersect. If x equals 1, then y would also be equal to 1, right? And so the limits of integration for y go from y equals 1/2 to y equals 1. And that's it. We're done. Notice we don't actually have a concrete function to work with, right? It just gives us a generic function f of x, y. If we had a concrete function, we might be able to actually integrate. But all this problem was asking us to do was reverse the order of integration. We have done that. We do not need to integrate for this problem. That's our final answer.